We move on. So what's the definite integral? We looked at indefinite integral. What was that? Indefinite integral is basically the antiderivative of the function. So indefinite integral is what? Is that a number or is that a function? Indefinite integral is a function. Definite integral is going to be a number. So let's see how we defined the definite integral in Calc1. What did we do? Well, let's say that f is a function, and the function f is defined. You're not going to tell me, right? You're just having fun. Forgot to do, huh? All right. So f is a function, and it is defined on the interval from a to b. And let's pick a partition P of that interval. So what do I mean by a partition? Partition means that that I have the interval from A to B. A partition of that interval basically means a collection of distinct points. A collection of distinct points from that interval. So here, the partition points are x0, x1, x2, x3, xn minus 1, xn, and the last partition point has to be B. The first partition point has to be A. Okay? And in this case, how many partition points did I pick? How many partition points did I pick? I have x0, x1, x2, up to xn, right? For example, if n is 100, right? If n is 100, how many partition points do I have? If n is 100, how many partition points do I have? And 1, because x1 up to x100 will be 100, but x0 will be 101. Okay? So if I pick any n, then I have n plus 1 partition points. How many? Now, once I pick these partition points, it divides the interval into smaller subintervals. How many subintervals do I have? How many subintervals do I have? Notice the first subinterval is between x0 and x1. The word first goes with the index of the right-hand point of the subinterval. First subinterval, the index of the right-hand point is 1, right? Second subinterval, the index of the right-hand point is 2. Second and 2 goes together, right? So first subinterval, second subinterval, right? Third subinterval, right? This is interval number. This is interval number what? It will be 100th or nth. This would be the nth subinterval because the interval number is the same as the index of the right-hand point. The interval number of the subinterval, right, is the same as the index of the right-hand point. Remember, once again, this is the third subinterval, and the word third goes with the index of the right-hand point x3. Okay? So this is the third, then this would be the nth subinterval, right? Nth subinterval. Now, in the middle, I am talking about there is a ith subinterval, right? Ith, where I is a number between 1 and n. So I am talking about the ith subinterval here. So ith subinterval would be what? Xi minus 1 and xi. Because the word ith goes with the index of the second or the right-hand point. So this would be the ith subinterval, xi minus 1 up to xi. Why do I use that notation, the ith subinterval? Well, the reason is, if I want to make a general statement about all the subintervals, I will say this is true for the ith subinterval. So when I say this is true for the ith subinterval, I mean it is true for all subintervals. Am I making sense? Is everybody clear? That's why I'm using that notation for the ith subinterval. Now, once I have this subintervals, then I pick sample points from the subintervals. So I pick one sample point, W1, from the first subinterval. I pick a second subinterval, a second sample point, W2, from the second subinterval, and so on. And Wi from the ith subinterval, Wn from the nth subinterval, right? W1 up to Wn, these are called sample points. Okay? And so what did we do? We divided the interval into smaller subintervals. From each subinterval, I picked a point. These are the W1, W2, Wn. Now I'm going to form a sum. What sum? Yeah, so in order to form the Riemann sum, this is what we're going to do. We are going to evaluate the function f at the sample point W1 and then multiply the value of that by the length of the first subinterval. So delta x1 here represents the length of the first subinterval. So f of W1 multiplied by the length of the first subinterval. I am doing so for every subinterval. I have a term, right? For every subinterval, there is a corresponding term here. For the second subinterval, evaluate the function at the sample point W2 multiplied by the length of the second subinterval. For the ith subinterval, evaluate the function at the sample point Wi multiplied by the length of the subinterval. Keep doing that until you get to the last subinterval. So in this way, you get a sum. And we can express that sum by using the summation notation. So how do I express this sum? By using the summation notation. Well, summation I going from 1 up to n, this tells you how many summons you have. The number of values of I tells you how many summons. So I is going from 1 up to n, tells you you have n summons. And then this guy is giving you the formula for the ith summon. Right? This is giving you the formula for the ith summon. Remember the ith summon? This is the ith summon. That's the ith summon here. So when I use this notation, I am basically saying, what is the first summon? Well, when I is 1, you get the first summon. When I is n, you get the last summon, right? The nth summon. Okay, so that's the meaning of this notation. This sum is basically expressed by this summation notation. And that's called the Riemann sum. So I use this notation here, Rf of P. This is the Riemann sum of f with respect to the partition P. The Riemann sum of f with respect to the partition P. Is that clear? That's the Riemann sum. So why do I care about Riemann sums? Well, let's first of all see geometric application of the Riemann sum. Let's say that my function f is a non-negative function, or just think about it as a positive function. And let's say the function is continuous, so the graph is a nice continuous curve between a and b. So on the interval from a to b, my function is continuous, positive. When it's positive, the graph would be above the x-axis, right? If the function is positive, the graph will be above the x-axis. So that's I have the graph of the function f. Okay. So I want to show you, what does the Riemann sum represent? What does the Riemann sum represent geometrically? So think about the summons of the Riemann sum. What was the first summon? The first summon was f of W1 multiplied by delta x1, which is the length of the first subinterval. geometrically, what does it represent? Well, what is f of W1? F of W1 is the height of the graph at W1, right? F of W1 is the height of the graph at W1. You agree with that? So f of W1 is this height, and then I am multiplying that height with the length of the subinterval, with the length of the first subinterval, right? F of W1 is the height of the graph at W1, and delta x1 is the length of the first subinterval. When you multiply the length with the height, you get the area of this rectangle, right? You get the area of the rectangle above the first subinterval with height equal to f of W1, right? So the first summand in my Riemann sum represents the area of the rectangle above the first subinterval having height f of W1. Same thing happens with the second summand, right? F of W2 multiplied by the length of the second subinterval, right? So that gives you the area of the second rectangle here, right? Am I making sense? So the third summand will represent area of another rectangle like this. The ith summand will give you the area of another rectangle like this, and keep doing that for the last subinterval as well. So what does it mean? So what's the Riemann sum then? The Riemann sum is the total area of this rectangle, right? The Riemann sum is the total area of these rectangles, right? So can I say that the total area of these rectangles is an approximation of the area below the graph of f above the interval from A to B? The area below the graph of f above the interval from A to B can be approximated by that Riemann sum, given that n is big, right? Now think about this. As n gets bigger and bigger, meaning that you have more and more partition points, would mean that the subintervals, you will have more and more subintervals, which would mean that the subintervals will get more and more narrow, right? They are shrinking. As n gets bigger and bigger, more and more partition points, more and more subintervals will mean that the rectangles are shrinking. So then the total area of these rectangles will approximate the area below the curve better, right? So the point is, look at the limit of the Riemann sum as you pick more and more partition points. As you pick more and more partition points, these Riemann sums will tend to a number, will approach a number. And that number is what we call the definite integral of the function f from A to B. Am I making sense? Look at the limit of the Riemann sum as n goes to infinity, meaning that as the subintervals are shrinking. As the subintervals are shrinking, the Riemann sum is going to approach a number, and that number is the definite integral. And in this case, that number would be the area. If I take the limit of the Riemann sum, that would be the area below the curve. Is everybody okay with that? So that's one reason why we care about the Riemann sum. So that's what I said here. The Riemann sum, if I look at the Riemann sum, it converges to the area below the graph of f above the interval from A to B as the subintervals are shrinking. This notation means as the subintervals are shrinking to 0. Am I making sense? The length of the subintervals are shrinking to 0. So that's one reason. There is another reason why you would care. Well, there are many examples, but let me give you another one here. Let's think about the mass of a rod, right? You have a rod, straight line, let's say, and once I have a rod, I can label the rod as an interval from A to B. Right? I can think of the rod as an interval from A to B. I can put it on the real number line and say that this extends from A to B, right? You agree with that? Whatever the rod is, I put it on the real number line, and it goes from A to B. And let's say the function f gives you the density of the rod. It gives you the density of the rod at any point x. The value of f is the density of the rod at x. What's the meaning of density? Density in this case means mass per length. If you have a two-dimensional object, density would mean mass per area. If you have a three-dimensional object, density would mean mass per volume. So in this case, it is density means mass per length. So f of x is the density function, okay? And given the density function, I want to find what's the total mass of the rod. Now let me ask you this. If the density is constant, if the density at any point is the same, what's the mass? How would you find the mass if you know that the density is constant? Yeah.
Take the derivative.
No. Let me ask you this: if I say that it took you 2 hours to go from here to Columbus, and you drove with constant speed of 60 miles, what distance did you cover? Your speed was constant 60 miles per hour, and you drove 2 hours. What distance did you cover? 120. What did you do? Multiply. In this case, I'm saying that the density is constant everywhere. Density is what? Mass per length. So if I multiply density with length, total length, I get the total mass. So total length multiplied by the constant density will give me the total mass, right? Do you agree with that? Now imagine that density is not constant. Density varies depending on what point we are talking about, right? So density is varied function. In that case, how would you define the total mass? Well, the idea is, okay, the density is not constant over the rod. So let's start out by doing the following. Cut the rod into small pieces. Okay? So let's pick n to be a big number, and then cut the rod into smaller pieces. So the first piece goes from A to x1, second piece goes from x1 up to x2, and so on. So we are just breaking the rod into small pieces. And then, because I have, let's say n is so big, billion, trillion, whatever you say, big, that these pieces are so tiny, right? If these pieces are very, very tiny, then I can assume that I can say that the density over that small piece is constant. Very tiny piece, so I can assume that the density is constant there. It's not, but I can assume approximately constant. So I can say f of W1 is the density of the rod at the point W1. But I can say that f of W1 is the constant density over the first piece. F of W2 is the constant density over the second piece, and so on. Am I making sense? So how would you approximate the total mass? Well, what is the mass of the first piece? The mass of the first piece is the length of the first piece multiplied by the density at W1. So multiply the density at W1, f of W1, with the length of the first piece, you get the mass of the first piece. Approximate. F of W1 is not constant density, but I'm saying if it is so tiny, then I can assume that approximately the density is constant. Yeah.
Is W1 the name of the interval?
No, W1 is a point.
On that interval?
In that interval, yeah. It's a single point in that interval. Yeah. So I evaluate f of W1 multiplied by the length of the first subinterval. This is the mass of the first piece. And I keep doing it for all these subintervals. So I'm adding those numbers, I'm getting an approximation of the total mass. Okay? But then, think about this. As I pick n bigger and bigger and bigger, these pieces are becoming smaller and smaller and smaller, which means f of W1, f of W2 are really going to be quite precise approximation of the constant density, right? I can think of f of W1 as becoming more and more like the average density of that piece. So then, as n gets bigger and bigger, this approximation is actually getting closer and closer to the actual mass, right? The Riemann sum is approximating the total mass, and this approximate mass is getting closer and closer to the actual mass as I pick more and as I pick n bigger and bigger. Am I making sense? So that's the total mass. The total mass is the limit of the Riemann sum as n gets bigger and bigger and bigger. Is everybody okay? Again, as n gets bigger and bigger, the pieces are getting smaller and smaller. So as the lengths of the pieces are going to zero, the Riemann sum is going to approach the mass of the rod. So that's another application of the Riemann sum. So what do we see? We see that the limit of the Riemann sum is an important quantity, right? The limit of the Riemann sum is an important quantity. And so we're going to give it a name. What name do we give it? I have the Riemann sum, and I take the limit of the Riemann sum as the lengths of the subintervals go to zero. Take the limit of the Riemann sums. Take the limit of the Riemann sum as the lengths of the subintervals go to zero. In other words, as you pick more and more partition points, you get smaller and smaller subintervals. Subintervals are shrinking. And in that process, the Riemann sum is converging to a number, and whatever that number is, that's defined to be the definite integral of f. So f is the density function, then the integral gives you the mass. If f is a non-negative function, this integral gives you the area below the graph of f, above the interval from a to b, right? Okay, now this limit that we are talking about, it may not exist for some function. Okay? In fact, it doesn't exist for many functions. Okay? Am I clear? So when this limit exists, we will say that the definite integral exists. When the limit doesn't exist, we will say that the definite integral does not exist. Okay? Now, if the definite integral exists, we are going to say that f is integrable. If the integral doesn't exist, then we are going to say that f is not integrable. Okay? Integrable versus not integrable. Integrable means this quantity exists. This quantity exists. Am I making sense? So we know for some functions it may not exist. For some function it will exist. So the question is, for what type of functions are we guaranteed that the definite integral will exist? Do we know that? And the partial answer is, if you know that the function is continuous or piecewise continuous, then if you know that the function is continuous or piecewise continuous, then you know that the definite integral will exist. I guess you guys all remember what continuity means, but piecewise continuity simply means that if I'm looking at f on the interval from a to b, it may not be continuous everywhere, but it may have finitely many jump discontinuities. If the function has only finitely many jump discontinuities, then it is a piecewise continuous function. Am I making sense? Now, jump discontinuity is not the same as asymptote, right? There is a difference between having a discontinuity where you have a jump in the graph, finite jump, versus a discontinuity where you have a asymptote, right? Those are different. So I'm talking about jump discontinuities here. In any case, all you have to remember, if f is continuous, the integral exists, okay, from a to b. Another important theorem that I didn't tell you, those of you who have taken Calc 1 with me, I didn't tell you this fact in Calc 1 because we didn't need it, but we are going to need it. I'm going to refer to this theorem later. If the definite integral exists, right? What's the meaning of that? Definite integral of f from a to b exists. It means that the Riemann sum of f from a to b converges, right? The limit of the Riemann sum of f from a to b exists, right? So if the definite integral exists, then we know that the integrand function f must be a bounded function. Okay? What's the meaning of a bounded function? When I say that f of x is a bounded function, it means that for any value of x, f of x is in between two constants. When I say f is bounded, I mean f of x is bounded, f of x is in between two constants for any x. Okay? Can someone tell me what will that tell you about the graph of f? What does it tell you about the graph of f? Can you tell me that? In terms of the graph, geometrically, what would that mean? So let's say this guy is the line y equals to capital M. This is the line y is equal to lowercase m. So what can I say about the graph of f? Let's say here is A and here is B. What can I say about the graph of f? The graph of f must lie in between those two lines, right? The graph of f must lie in between those two lines, right? So that's what it means to say that f is bounded. It means that the graph of f must be in between two horizontal lines, right? You guys agree with that? On the interval from a to b. We are talking about the interval from a to b. Okay, that's what it means to say that f is bounded. So again, the theorem says if the definite integral from a to b of f exists, then the function f has to be integrand function, f has to be a bounded function. What's the contrapositive of that? No. The contrapositive is almost there. The contrapositive is if f is unbounded, so you're looking at the negation of the... So here, when I have this if-then, the condition is this, the conclusion is this. Now you're going to reverse it, but negate it. You're going to negate both statements. So now instead of saying f is bounded, you're going to say if f is unbounded, then the integral will not exist. That's the contrapositive. And they are logically equivalent statements. When I say if the integral exists, then f is bounded, that statement is logically equivalent to saying that when f is unbounded, the integral will not exist. But if I say if the integral does not exist, then the function is unbounded, that's not equivalent. Okay? Is everybody okay with that? You should think about if-then statement as like a promise, right? It's like a promise. If you get a 90%, then I promise I'll give you an A, right? If you get 90%, I'll give you an A. That's the promise. So if you violate the condition that maybe you got 88%, right? I can still give you an A. Am I making sense? Does that make sense? So think of this that way. All right, well, I'm going to come back to that theorem later. But let's move on. There are two things that you need to remember. One is, if I have a non-negative function over an interval from a to b, then I can talk about the area below the graph of f above the interval from a to b, and that area is given by the definite integral from a to b of f of x dx. Right? That area is given by the definite integral. However, what if the function is not non-negative? What if the function has positive and negative values? For example, what if I have a function where the function looks like this? There are some positive and there are some negative values. In that case, geometrically, what is the meaning of the definite integral? Well, you look at the area, look at the interval from a to b, you look at the area between the graph of f and the x-axis. Between the graph of f and the x-axis. So you are talking about the area A1, area A2, area A3. What is the meaning of the definite integral? The meaning of the definite integral is net area. Net area means A2 that I have, A1 minus A2 plus A3. That's the value of the definite integral. That's what I mean by net area. I am subtracting the area which is below the x-axis. Right? So the definite integral always represent, geometrically always will represent the net area if you have a function like this. Is everybody clear with that? Very quickly, an example. Let's say I have the integral from 0 to 3 of x minus 1 dx. Now, everybody here, I know you can evaluate that by using the power rule, but let's try to evaluate this by using the previous fact. What's the integrand function here? The integrand function here is this function here, right? That's the integrand function. And what's the graph of that integrand function? The graph of that integrand function is this graph of this equation, right? Y is x minus 1. That's the graph of the function. So the graph of the function is a straight line. And that straight line is this line that I have drawn here. So I have drawn this straight line, the graph of the function, integrand, between 0 and 3. So I drew the graph of the integrand between 0 and 3. Why is it 0 and 3? Because the integral goes from 0 to 3. And then I look at the area between the graph of the integrand and the x-axis, and I see that there are two areas, right? A1 and A2. A1 is below x-axis, A2 is above x-axis. So what's the net area? The net area is A2 minus A1, right? Okay, what is A2? A2 is a triangle, so the length here, the base is 2, the height is 2, right? Half times base times height, that's going to give you the area, right? So the area of this triangle is 2. The area of this triangle is what? Half. The base is half, the height is half, the base is 1, the height is 1. So half times base times height, which would be the area. So the area, the net area in this case is coming out to be 3/2, which means that's the value of this definite integral. It is giving you the net area. You can calculate this definite integral by using the power rule and so on. You'll see that you get the same answer. Everybody's okay with that? All right. I'm not going to go over this here. This is just another example. If you have a time interval from A to B, and f of x is giving you the speed at time x, the speed of an object at time x, then the definite integral of f from A to B is giving you the distance, the total distance covered over that time interval. And again, you'll see that the Riemann sum is an approximation of the total distance, and the Riemann sum converges to the total distance as the number of partition points goes to infinity. Okay, so let me just skip that. Let me remind you two algebraic properties of the definite integral. They are the same as the ones we had for indefinite integrals. Remember, these two properties hold for indefinite integrals as well. So integral from a to b of c f of x dx, right? If you have a constant factor, you are allowed to take it outside of the integral. Constant factor. Okay? If I have a c plus, right? If I have c plus, I cannot say this is the same as c times that. Okay? C times this, I can factor out the c. The second one is saying that if I have a sum, I can take the integral term by term, right? I can take the integral one term at a time. We always use that. We just sometimes you don't even think about that we are using these two algebraic properties. Everybody's okay. Now, let me do an example here very quickly. The integral from 0 to 1, 3x squared plus the root of 1 minus x squared dx. What is that integral? Well, by using the second property, I can integrate term by term. So I can take the integral of the first summand plus the integral of the second summand, right? And then I look at the first integral now. I see that there is a factor of 3. That can be taken outside by applying property 1. I get the integral of 3x squared is the same as 3 times the integral of x squared. And the second integral, I write it as it is. And then finally, I'm telling you that the value of the first integral is 1/3. The value of the second integral is pi over 4. You might say that, how did you know? I'm pretty sure you know how to evaluate the first integral by using the power rule. The second integral, you may not know. How many of you know how to compute the second integral? Well, there is some sort of substitution that you could do to evaluate it, but that technique you haven't learned. But if you took Calc 1 from me, I did show you how to compute this integral. How? By interpreting it as an area, right? So if you look at the integrand function is what? Root of 1 minus x squared, right? So I look at the integrand function, root of 1 minus x squared. What's the graph of that? Can you tell me that? The graph of that is it's the upper half of the circle, right? It's the upper half of the circle. So the upper half of what circle? The unit circle, right? Radius is 1. Look at the upper half of the circle. But you are going from 0 to 1. X is going from 0 to 1. So you're actually looking at 1/4 of the circle. So what's the area below 1/4 of the circle? It's basically 1/4 of the area of the entire circle, right? The area of the entire circle is pi times r squared. R is 1, so pi divided by 4. That's the area below the graph of the integrand between 0 and 1. Okay, that might not have made much sense because I didn't draw anything for you, but you can evaluate that by using the geometric interpretation of the integral. However, later on in this course, you'll see how we can handle an integrand like this by using certain types of substitution. Okay, so we're going to get there very soon. 2 more minutes, so let me just remind you 2 more things. What's the integral from a to a of f of x dx, no matter what f is? 0. Very good. If I am looking at the integral of a constant function c from a to b, what do I get? C times b minus a, right? I get c times b minus a. You can apply the power rule to see that. right? Or you can say that what's the antiderivative of c times x, right? And then you use that. But I haven't reviewed those concepts here, but you can figure out that the integral of c dx would be c times b minus a by just looking at the geometric interpretation of that. Okay, so I will let you think about that and end here. One more thing. So far we talked about the integral from a to b, right? The integral from a to b where a is less than b, right? We talked about the integral from a to b where a is less than b. The lower limit is smaller than the upper limit. That's how we define Riemann sums and so on. But it is convenient to be able to talk about integral where we go from b to a where b is bigger. So if I have the integral from b to a of f, that's the same as the integral of a to b, but you have to introduce a negative sign in front. So for example, the integral from 1 to 0 is the same as the negative of the integral from 0 to 1. Okay? It's like thinking about the following problem. If I am integrating, let's say the integrand is the velocity function. So if you are going from time 0 to time 1, integrating the velocity, you're getting the net displacement, right? But now if I say, well, go from 1 to 0, then you're basically looking at the reverse path, right? So now you're saying the net displacement is negative of whatever displacement you had from 0 to 1, right? Okay, so let's stop here.